You ready for this? I think you're ready for this. We're ready. I'm ready for this. You ready for this? We're going to do some standing waves here, all right? First thing we're going to do is talk about standing waves in a string. And we're going to talk about kind of the basics there, which is going to give us the right ideas for the fundamental frequency and the harmonics and things like that. And then we're going to go talk about standing waves and pipes. Okay, now we talked about a little bit of this in class. You know, we looked at the blue and the green waves and how they matched up together to give us the superposition of the wave that's just kind of going back and forth. Remember that standing waves are going to happen. Sorry that it got a little bit of reflection there. Standing waves are going to happen when we got a wave going one direction and a wave going the other direction and building up. They're exactly the same waves so that I keep getting kind of this maximum minimum where that wave is standing in place, or where a wave's coming down and reflecting back the other direction, much like you did with the slinky lap, right? So one of those two things has to be happening here in order for that to happen. Now, let's talk about the simplest situation first. Simplest situation first was that first one where you did that fundamental frequency where it was just going kind of back and forth, and you ended up having the slinky all in one direction at one point in time, and then a short time later, you had the whole slinky on the other end like this, or the string. We did this in the vibrating string lab as well. So this string is going up, and then it's going down, and then it's going up based off of whatever's causing the vibrations, right? You got nodes at the end, you got an antinode here in the middle, which is the place where it's not at a node. And so notice that every single point along this curve is moving in the same direction at the same time, okay? Not at the same rate, right? The big one has to go higher, the one in the middle is gonna go higher. These other points aren't ever gonna get that high. Only that point will go up that high and down to the very bottom. All of the others will move in phase, they'll move up and down at the same time, but they won't be moving as far, right? It's not like a transverse wave, not like one of those, the traveling waves where every single point gets to go all the way up and all the way down as that energy is transporting from one place to another. This one, the energy is standing there, going up and down, up and down, up and down. Okay, so at this is what's called our fundamental frequency, or the first harmonic. Okay, now let's relate this to the wavelength and the frequency. Okay, so we know that the speed in this specific string, this string is our medium, is going to have a specific velocity. Okay, now that velocity will be important when we find the frequency, because what I can get here is I can get the wavelength, right? I can see that I'm going from a node up to the top, down to the middle, which is half of a wave, right? I still need to go down to the other side. So this is half of a wave. So if the length of my string is L, then the wavelength here is 2L, right? The wavelength goes from one node to the other node, and then it's got to go that far again before I complete a full wave, all right? Now, the frequency then is, remember that velocity is equal to wavelength times frequency. So frequency, if I divide by the wavelength, frequency equals velocity divided by wavelength. So frequency here is the velocity divided by 2L, okay? Let's look at the next one. The second harmonic is where I get two antinodes with the string, okay? This is going to be important. The idea behind where we're getting that harmonic and things are going to be important when we get to the pipe, because there's one of them is going to be a little bit weird, a little bit different. And I'll show you that in just a second. Yeah, I'm almost there, all right? So here we go. We've got this one will have two antinodes. You've got an extra node there in the middle. Again, everything here moves up at the same time. Everything there moves down at the same time. Everything there is in phase with each other. These are in phase with each other. However, adjacent antinodes, this one and that one, are out of phase. In fact, they're pi out of phase, or 180 degrees, however you want to describe it. But they're completely out of phase. When this one is going up, this one is going down. And then when this one goes up, that one will be going down, right? So this wave isn't moving this way. The string is moving up and down like this, all right? Now, this is our second harmonic. It's our second harmonic for reasons that we'll discuss in just a minute. Right now, it's okay to say, well, I've got two antinodes, all right? That makes sense for a string. It won't make as much sense when we start to look at the pipes in just a minute. But this is our second harmonic. Again, in this situation, my wavelength, note that from one end of the string to the other, I now go through a full wave. So the wavelength is just the length of the string, okay? The frequency then is the velocity divided by the length of the string. No problem, right? Okay, let's move on to the third harmonic. We get to the third harmonic, and it's going to be very similar. We now have three antinodes, right? 1, 2, Great. Most of you are comfortable with this idea by now. Noting, again, that it goes up and down. Note that these are all going up, these are going down, those are going up. So again, adjacent antinodes do the opposite at the same time. Okay? But because they're always doing the opposite, you always end up with this thing that when it moves fast enough, it looks like everything's doing the same thing at the same time. Okay, so there we go. We'll go with our wavelength. Note that this time the wavelength's a little bit different. Wavelength's a little bit strange this time because it doesn't go all the way down. It only goes 2 out of 3 of those areas. So we're going to say that it's 2/3 of the length. All right? That right there is one wavelength, going up to a crest, down to a trough, and back to the middle. That's one wavelength. Okay? So the wavelength here is 2/3 of the length. Now, the frequency then is the velocity divided by 2/3 of the length. You may think that's weird, and it is kind of a little bit weird, but you'll see how that works in just a second. All right? So let's move on. Fourth harmonic. 1, 2, 3, 4. All right? And same thing here. Okay, moving up and down. Again, we can get our wavelength, which is now only half, right? Because it takes up 2 of the 4 segments, right? Going from the middle up, middle down, back to the middle. So 1/2 of the length. And the frequency then is V divided by half of the length. Now you look at that and you say, well, frequency sure is messy. I'm going to show you something really quick. Okay? Let's look at this a little bit deeper. Okay? Let's throw some numbers in, okay, to help make this kind of connect, make sense a little bit more. All right? So let's say for a minute that this string has a velocity of, let's just say 10 meters per second. That's how fast the wave moves through the string. Okay, we're going to say that the length for simplification is 2 meters. You can do this with any numbers. It really doesn't matter what numbers you choose. This same idea is going to work because of the ratios. Okay, but these are just the numbers that I just happen to come up with right now. No, I didn't even think about it ahead of time. Okay, so we just got 10 and 2. So when I look at this one, the fundamental frequency, the first harmonic, my wavelength is 2 times the length. That was 2 meters, so therefore my wavelength is 4 meters, right? My frequency is the speed divided by that. So obviously I didn't think about this very much because I got 10 divided by 2L, which is 4. So 10 divided by 4, which is 2.5. Okay? Check me on a calculator if you want. Go ahead. I'm a math teacher as well, so I'm pretty comfortable with it. Let's move on. Okay, second harmonic. Lambda is L. Okay, so this time the wavelength is the whole length of the string, which is 2 meters. So we're going to go 2 meters. The frequency is the speed divided by the length. Okay, so 10 again, divided by 2. 10 divided by 2 is 5. Now remember, frequency, sorry I didn't write the units up there, frequency is in hertz. Okay, how many cycles you go through in a second. Okay, moving on to the third harmonic. The length is now 2/3 of the length. So 2/3 of 2 meters are starting to get a little bit messy, so that's 2/3 times 2, which is just going to be 4/3, which is 1.3 repeating meters. All right, so not as nice anymore. I'm starting to get into some decimals here. What happens then to the frequency? Well, the frequency will be 10 divided by that. Now go ahead, do 10 divided by that. Okay, I'm going to do it right here on my calculator. I'm going to go 10, because I've got a calculator, I may as well use it. And so that I can show you so that you believe me, I'm going to go 10 divided by 4/3. And what do I get? What do I get? I got 15/2, which is 7.5. So 7.5 hertz. All right, now let's look at the last one. The last one here, lambda is now half of the length of the string. So lambda, the length of the string is 2 meters, so this lambda is going to be 1 meter. What is the frequency going to be? Well, it's going to be V divided by half of the length. All right, so V divided by half of the length, well, that would be 10 divided by 1, which is 10 hertz. Okay, so I calculated all those using the formulas that we just came up with, okay? But recognize that I could have just gone to any one of these and worked with it, right? I don't have to go through every single one of these. If I want the fourth harmonic, I draw the picture of the fourth harmonic, And then I take the equation straight from there. I get the wavelength from there. I use the speed. I get the frequency from there. No problem. Okay? One thing I want you to notice, though, is that the wavelengths are kind of doing something weird, right? It goes from 4 to 2 to 1.3333 to 1. It's the difference every time is changing. Look at the frequencies, though, and this is important. The frequency starts at 2.5 hertz. The second harmonic is 5 hertz. The third harmonic is 7.5 hertz. The fourth harmonic is 10. Do you notice anything happening there? Some of you say, yeah, I'm going to add 2.5 hertz. Yeah, where do we see the 2.5? It's right here. You add that fundamental frequency every time you go to the next harmonic. Okay? So this is defined as the second harmonic, not because there's two antinodes. It's the second harmonic because it is 2 times the fundamental frequency. It's double that. This is defined as the third harmonic, not because there's 3 antinodes, but because this is 3 times your fundamental frequency, right? Whatever the relationship is to this initial frequency, that is the definition of your harmonic, okay? That's going to be really important when we get to the pipes in just a moment, okay? So hopefully that makes sense. Here, take a look at my kaleidoscope while we move on to the next. Now, I know what you're thinking. You're thinking one of 3 things. Number 1, that was amazing. Or you're thinking, man, Mr. Bywater is an amazing artist. Or you're thinking, man, that guy is crazy. And you know what? All 3 are correct. Yeah. All right, let's move along. We're going to look at standing waves now in pipes. Okay? Now, standing waves in pipes are going to be slightly different. Okay? Same principles, but we have to think about it, draw it a little bit differently. Okay? So I've got 2 sets of pipes here, right? These pipes are the open pipes. You can tell because it's open on this end and it's black, so it's closed on that end. These pipes are open on both ends. Now, in both of these situations, we're going to be able to get a standing wave. Okay? Now, first we're going to look at the standing waves in a closed pipe because that's what you did in your speed of sound lab when you were looking at the tuning forks, which the sound went down in the pipe, bounced off the water, and came back. Okay? Now, first, principle when you're going off of a solid wall. Now, that's going to be a reflection with a fixed boundary. Okay? Now, remember what happened with the slinky when you sent it down and you were holding it, and what happened to the wave when it came back? Did it come back on the same side? No, it didn't, did it? It came back on the other side. Okay, it reflected on the other side. So the same thing's going to happen with your wave here. All right. Now, another thing that you want to make sure to recognize here is that we're drawing, remember, a standing wave that's being created in this pipe. Okay. In order to get resonance, this point this is where you're listening. Here's your ear. Yes, like I said, amazing artist. There's your ear listening to the pipe. In order to get that resonance, in order to get that sound, you need to have a point where here at the opening, these particles are in a standing wave going from a maximum to a minimum at that point, vibrating up and down. So the reflection or the waves passing through there have to be in such a way that it goes from maximum, minimum, so that you have the maximum amount of constructive interference possible. Okay? So in order for that to happen, the sound is going to come in. Remember, sound is a longitudinal wave, so it's actually vibrating back and forth, but we're going to denote it here with a maximum, minimum this way. So remember, these particles are actually traveling this way, forward and backwards, not up and down, but the wave we draw is going to represent that just because it's easier to visualize. Okay? So it's going to start at maximum here. When it gets to the wall, it's going to reflect. So what we're going to do is we're going to start at the top. We're going to go down to the middle right there. It's going to reflect off the wall. It's going to have a node at this end, and then it's going to come back to this end because it's going to come back on the other side because of that reflection. Okay? Just like what we expected with the slinky. Now, notice that I went the full length of the tube and back with my wave, so that reflected wave, and it's gone from a maximum down to a minimum. Now, if I draw my wave, the maximum to the minimum is how much of that wave? Sorry, big fat head. Maximum to minimum is how much of the wave? It's only half of the wave, right? And so going down and back was actually only half of a wavelength. So in this case, if my pipe has a length of L, what is the wavelength going to be? The wavelength is going to be 4L. 4. 4L, right? Because that will be 1, that'll be L, 2L, goes through half a wave. So then I got to go through a whole other half a wave before I get to a full wavelength. So a wavelength is 4L. That's going to be my fundamental frequency, all right? So then frequency, of course, is going to be V over that number, 4L. Okay, simple, straight enough. All right, now using the principles from earlier in this video, right? Okay, so let's move on to the next one. Okay, so we have to hold to the same principles, right? We have to go from a maximum. It's got to come. It's got to flip here, and then it's got to go back to the other side. You can't go up to a corner. Okay, let me show you. I'm going to use red here because red is bad, and so I'm going to show you what would happen if I start here and I go down to the bottom there. What would happen if I went to the bottom there? Well, it's going to reflect back, and it's going to go back to where it started from, right? Because it's fixed at this point. And so when it reflects back, it's going to reflect back to where it came from, which means you're not getting the resonance. You're not going to get anything. So therefore, it can't do this. Okay? It's going to have to get rid of the red. Red is bad. Okay? So it's got to go from here. It's got to go down and then back up to that point. All right? And then from that point, it's going to go the opposite direction, just like it did with the slinky. And so now the wave's going to come back this direction, just like that. Now, this time, how long is a wavelength? This is going to be a little bit harder. Okay? This is L. How much of a wave am I getting through in that L? Well, I'm going from a top to a bottom and back to the middle. Let's look at our wave. Top to bottom and back to the middle. That's just one path, right? Just going length. That was top, bottom, back to the middle is 3/4, right? So one length here is equal to 3/4 of a wavelength, right? Top, bottom, back to middle. I just got to get back to the top to finish a wave. So that means that my wavelength is equal to, just flip the fraction, 4 over 3 L. And of course that means that my frequency is equal to V over 4/3 L. Got it? Let's move on to the next one. Okay, let's see what, again, same principle. It's got to start at the top, go to the bottom. It's got to have a node here so that it reflects back properly to get that standing wave. Okay, so this time, it's going to go down, and then up, and then I can go to the middle, right? So I passed the middle once, twice. This time I didn't pass the middle at all before I got there. That was just the first time I could go to the middle. This went through the middle. That was the second possible time I could get in the middle. Now this is the 1, 2, third possible time I could have been at the middle of that pipe. Okay? Reflects back in this direction, and you'll notice that I get that. Okay? So wavelength equals, can you see it? Can you see it? I go from a maximum to a minimum back to a maximum. There's a wavelength. Okay? And then notice I got an extra quarter there. Okay, so in this case, the wavelength is going to be 4/5 of the length. And frequency is velocity over 4/5 of the length. Okay, 1, 2, 3, 4, 5. 4 of those were that wavelength. Okay. You can do a similar thing to what we did up here if you want. If that's too much to think of it that way, you can say, well, I see 1 1/4. So a length is 1 1/4, or 5 over 4 waves. Right? One length has a full wave and then an extra quarter. Okay, and if that's the case, reciprocate, wavelength equals 4 over 5L. Frequency is that. Okay? We're not going to do the last one because I want to keep this video a little bit shorter, but that's how you get it. Now, I haven't named the frequencies yet. There's a reason for that. I want you to see what happens. Okay? Go ahead. Choose a number for L and choose a number for V. But use the same number for L and V for all of these. Okay? If you want to use the same number as we did for the string, fine. So be it. If you don't want to use the same number, then don't. Okay? This time, just to show you that I can be different, I'm going to choose a length. Let's go a velocity of 20 and a length of 5. Okay? Go ahead and see if you can calculate each of these. Okay? I'm going to go through a little bit quickly. If you can't follow along, just pause it. It's fine. Okay, but I just want to get through and see if you can figure out how this works. All right, so the wavelength is going to be 4L, which will be 20. 20 divided by 20 will be 1 hertz. All right, 4/3 of L would be 20 over 3 meters. Okay, the frequency would be the velocity, which is 20 divided by 20 over 3, which is 3 hertz. Again, you can pause this and work through the math on your own. Use your calculator, whatever you need to. Okay, this one is 4/5 of L. So if L is 5, 4/5 would be equal to 4 meters. The frequency would be would be the velocity of 20 divided by 4, which is 5 hertz. Okay, we could keep going. Obviously, we could go to the next one, but like I say, in the interest of time, let's just see what happens here. Okay, look at the frequencies. It starts at 1. The next one is 3. Now, what does that mean? That means that this is not the second harmonic, because remember, the second harmonic comes when the frequency is the frequency times 2. Right here, I have the frequency times 3. What that means is that this is the third harmonic. This is still the fundamental, or the first harmonic. This is the third. Note that this one goes up to 5. That's 5 times the fundamental. That means that this is the fifth harmonic. Okay. That means that for a closed pipe, only the odd harmonics are actually possible. The even ones can't happen. Okay, now this is, for a lot of people, very confusing because they want to say that everything exists. Well, it just doesn't. You have to recognize that that even harmonic is not going to exist. In order for the even to work, you have to be able to have this point where it gets from one side down to the other side, but you can't do that with the fixed end. The fixed end has to be a reflection from that point. Okay? Let's look at the open pipes. Where'd I go? Just kidding, I'm still here. Let's move on to the open pipes. All right? So, again, like I say, going to be a little bit different. We're going to start with the first one. The open pipes, now, they don't have the closed end. Because they don't have the closed end, they don't have this fixed point that they're going to reflect off of. Okay, which means they're not going to bounce back on the other side. Because it is free to move, then it's going to be allowed to have an antinode at that end. Okay, so in addition to my ear, do this more or less the same. My ear here, yeah, I know, it's a beautiful ear. The ear here, which has to have the antinode to hear it, similar on the other open end, you've got to have an antinode there as well. If you don't have an antinode, then you won't get the resonance, the maximum resonance possible, and so you won't get the right sound. Okay, so the fundamental frequency then is going to occur when I have a maximum here and a maximum amplitude or displacement there. Now, the easiest, simplest way to do this is just go from the top, from a crest, down to a trough, and then as it resonates, it goes back the other direction. So again, bounce back and forth, but again, not this way, we're going this way because it's sound, it's a longitudinal wave. So you can look at that, and you can say, well, now I know then that my wavelength, because I go from a maximum to a minimum, I'm going through half of the wave there in that length, right? So therefore, the wavelength is going to be 2 times the length, right? The frequency then is going to be V divided by 2L, okay? You should be comfortable with that idea now. We've done it a couple of times. Okay, let's look at the next situation, right? The next situation, again, has to have that same idea. So the next easiest situation, rather than going from the top to bottom, would be to go down and then right back up to the top. Okay, that's the next easiest way to get that open resonance on both ends. So we're going to go from top, down to the bottom, back to the top, dotted here. Okay, just like that. And so my wavelength here, notice that I'm going through a whole wavelength, going from the top down to the bottom, back to the top. So that's one full wavelength that I was able to accomplish in the length of that pipe. So the wavelength is going to be the length of my pipe. The frequency is V over L. Again, notice I'm not memorizing these formulas. I'm drawing the picture, and from drawing the picture, I'm able to come up with these formulas. I don't have to go through the first, second, third, fourth one. I can choose any picture, any harmonic, and I can draw this picture from that, just from knowing the number of the harmonic. Okay? from recognizing that the fundamental here is a quarter of a wave, and from recognizing here that the fundamental is half of a wave. And then you can draw any harmonic from that point. Okay? So this I went through 2 half waves. This I'm going to go now through 3 half waves, right? So I'm going to go from the top down to the bottom, back up to the top. That's what I did last time. So I'm going to go one more time, back down to the bottom. And then this will reflect in the opposite direction and give me exactly the same thing there. Okay, this time, note that I've gone through 1 1/2 waves. Okay, so a lot of you will be easier for you to think of it by saying the length equals 1.5 waves, or better yet, 3/2. And if that's the case, then lambda equals 2/3 times the length, and the frequency, of course, is the speed divided by 2/3 of the length. Now, let's go ahead and check that out, make sure that it works. All right, so let's use the numbers that we had last time, because they worked last time, we may as well use them. So I've got a length of 5 and a speed of 20. So here, my wavelength is going to be 2 times the length, so 10 meters, and the velocity divided by that 10 meters is going to be 2 hertz. So we noticed something different already, right? Because I needed a longer wave for that fundamental, that meant that my frequency is going to be higher there, right? So, sorry, not a longer wave. It's actually be a shorter wave because I've got to go through more of the wave in that short length. Okay? Here, the wavelength is going to be the length of the pipe, which is 5. And so, therefore, the fundamental frequency is going to be 20 divided by that 5, which is 4 hertz. And then here, the wavelength is 2/3 of the length, so 2/3 of 5, that would be 10/3, which is 3.333 repeating. And then I'm going to go the 20 divided by that. 20 divided by that is going to give me, sorry, that was in meters. This will give me 6 hertz. Check it on the calculator if you want. That's fine. I have no problem with you doing that. So go ahead. You got this. Notice again, this time, 2 hertz, 4 hertz, 6 hertz. So this is the fundamental. Which is your first harmonic. This one, notice that 4 is the fundamental times 2. That makes this the second harmonic. And this one is the fundamental times 3. And so therefore, this is the third harmonic. So much like the string, with an open pipe, you can get all of the harmonics. With the closed pipe, you can't. All right? That's all. Hopefully that's enough to at least get you started, get you an idea of what you should be looking at and thinking about with respect to these standing waves. And maybe you can go work a couple of problems.